Okay.
Hmm?
I know, right? Danke. Okay, so in regards to the lab, which is due Tuesday, in general, on your labs, the way things should work is the cover page, the top, all right, as you will, if you will, which is the last thing that you're doing, and technically the only thing you should have to do at this point. This will have a few things. First, at the top is an abstract. An abstract is kind of like a short little couple of sentences that describes what you did, why you did it, and how it went. Okay, in very brief fashion. So from reading your abstract, I should get a quick sort of Polaroid snapshot of everything that went on. Not specifically, but just in general. You know, Polaroid pictures are not high resolution. The color is a little bit weird. That sort of stuff. That's fine. That's that's what I want. So something like we were supposed to determine the velocity of an object falling to the ground from a certain height. We approached this way. We got some results. Our results were not very good. Our results were pretty good. Our results were bad. Our results were great. Just something to kind of give me a feel of how your whole thing went. Then we do the error analysis. Okay. In the error analysis, there are two components of error analysis. The first one is quantitative error analysis. Now, a quantitative error analysis means, what does quantitative mean? Yeah, with numbers. So you're going to show your instrumental uncertainty, you're going to show your experimental uncertainty, and you're going to show something I like to call percent error. What's that? What is percent error, you ask? Let me show you. Percent error comes from this equation. Now, what do those variables mean? Well, let's take a look. A means actual. So the actual value. What is your actual value? Should be something like this. The value that you the value that your object should have been going at when it hit the table or hit the floor or whatever is 2gh, square root of 2gh. H being the height it fell, g being gravity. So this is going to give you an actual value. Then O is your observation. Okay, your observation is simply what value of velocity did you get. So it's kind of yours minus actual over the actual times 100%. And that's going to give you a percentage. You don't talk about the numbers in quantitative. Quantitative, you simply show the numbers, right? And then qualitative. And this is where you talk about stuff, okay? The first thing you're going to talk about, or the first thing you're going to do is use the numbers. Our lab went very well because our experimental uncertainty was less than our instrumental uncertainty. That indicates that we were preternaturally effective in the execution of our lab because we somehow defied the laws of statistics and got a better result than our instruments should have allowed us to get. Okay? In terms of our consistency, that's what your experimental uncertainty is about. It's kind of like standard deviation sort of thing. Then I want specific sort of sources of error. So in past labs, you get things like, oh, we tried really hard, we did the best we could, blah, blah, blah. Those kind of statements are stupid. Obviously, you tried hard. If you didn't, you wouldn't have done it. Obviously, you did the best you could, because if you were the kind of person who half-assed any random task, you wouldn't be in this classroom. You would be in integrated science. It's true. I love those kids too, but it's true. Okay, so don't tell me stuff like that. Tell me things like, on the third trial, we had an outlier because, I don't know, Casey from the other group bumped into, our timer right when they took the time. We didn't think that was a problem then, but once we graphed everything, we saw that there was a problem. We saw that it screwed up our result. Right? Remember, this isn't like chemistry. Chemistry, people cook the numbers. Right? You know what you should get, so you make sure that all of your data matches that, so you get the right answer, so that your error is low enough that you get a good grade. This class, I don't care what your error is, I care that you know why your error is that way. Okay, and I want specifics. So when I look through your data set and I see some wild, crazy data points, I want to know why that's that way. Okay, now do you realize what that's pushing for? Right? Do you remember when I told you to take logs as you go through your experiment? Do you remember this? Okay, good. Some people are shaking their heads. The other period was like, what? We've never heard of this before. Yeah, so as you're going through the experiment, be aware of what's going on. Right? So when Tim's doing trials, bam, 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 and not everybody in the group is doing the trials. Maybe, is it Evelyn? Yeah. So if Evelyn's in his group, she's taking the logs, right? She's writing stuff down about what's happening. And she notices that one trial went bad because something happened. She writes that down. Now, when you go to do this, and of course she shares that with everybody, you have a specific reason as to why that data point wasn't acceptable, right? That is super important in science, to be able to follow your process through the whole thing, to be able to catch any mistakes as you go, and like deal with them. Yeah.
So let's say you're doing a trial, and then you know you messed up somewhere, you should restart, you just continue on.
Like if you're doing like a run of trials, like 5 or something, and like you drop the ball, or like somebody started and you didn't drop the ball, and then you finally drop the ball, so it adds like a trial of like 10 seconds. Those sort of things you can sort of say, okay, that's just, we won't use that. That's done. But if you're doing the trials and you think something's right and you see one that's like crazy, when you're recording it, I don't know, maybe Evelyn's recording and she's like, whoa, this time is really weird. If you're being aware, then you stop and say, okay, everybody, what happened? And then you can write down what happened. And there's no need to throw out that trial because you thought it was fine in the first place. But if something breaks down in the procedure and you get a weird number, yeah, just do it over. But if you follow the procedure and you get a weird number, you shouldn't just throw that away. You should then try to figure out, because that specific trial might be trying to point you to the fact that you need to change your procedure. Does that make sense? I mean, basically, you don't want to be cherry picking your data points to get good data, right? You just want to use your procedure. So if the error is, if you didn't execute the procedure for some reason, drug sniffing dogs, everybody out, okay, well that one ball drop took 15 minutes. Well, okay, that's good. Right, that doesn't count. But yeah, but if you are using your procedure and you get a wild piece of data, just try to account for it. Why did that happen? Think about what are the things that cause error in your experiment, how did that affect it? All right, so yeah, also when you use the numbers, make sure that you're dealing with like, our percent error was, I don't know, we were only 10% off the actual value. Again, our instrumental uncertainty is 20%. So I think we did a great job. See, you're using the numbers to substantiate your statements. Right? Don't say we had a 10% uncertainty, we were awesome. Because what if your instrumental uncertainty is 1%, even a 10% error? Yeah, that means that wasn't great. You should have had something akin to 1%. Okay, questions about that part? Yeah.
For the quantitative, do you want us to show the calculations? Like
Yes. Show calculations. Now, let's say you have, let's say you had several setups or whatever, and you need to do an instrumental uncertainty, or you have a bunch of different trials at different heights, so you need to do experimental uncertainties at those different heights, or whatever. Or we do a volume thing in here. Yeah, let's say you did a volume on the aluminum block and you did a volume on the copper block. So you needed different things. If you're calculating the same thing, you don't have to show me 10 different calculations. So if you're doing one calculation but 10 different times, just show me the one calculation, and then the rest just put in the data table. So make sure that these quantitative things, a data table would be really helpful. Which is nothing more than, 4 columns, 2 rows, 1 column, 3 rows, whatever. Just something simple. Okay, now, what goes behind this? Right, all the other pages. This is like your original page, right? On that original page, we did observations, we did investigation, right? Oh yeah, and as a part of this, whenever we start a new project, investigation will include text notes. But that'll be a separate homework. But you'll do text notes whenever we start, so that you have your text notes as a reference, right? I think on here you had to write your procedure, right? Remember that paper? And also on here is your logs, right? That's this paper. And this might be multiple pages, that's fine, okay? Then this one is probably your graph. I don't know if that paper is. Some random stuff there, I don't know. But it's all by date. Newest on top, oldest on the bottom. So it's like by walking back through this, I can see your entire process. I can see what you did from day one. Yeah. Was the one that was stamped the one you turned in? Oh, okay. It was for Excel, right? Yeah, that's that one. Just staple them together. Because the graphs are also the same way. If you had to do the graph 5 times, you just keep stacking it up. Yeah. So if you did one graph, cool, good on you. Put it right there. If you did 2, then put the new one on top and the old one on the back. Basically, you never want to throw anything away and start clean. That's not what you want to do. You just want to have the process. The process is more important than the product. That's just generally true about life. Not about money. Money, it's all about the product. But the living part of life, it's all about the process. All right, questions on that? Okay. Then, so, what do we have on Tuesday? The lab's due. And quiz time. Let's talk about Wednesday. Wednesday, you need a procedure to determine V0 of a projectile. And you will have exactly one piece of equipment, a ruler. But of course, I don't know if this is equipment, but this is the test subject. This is your projectile launcher. That's it. So you will launch something from this, and then once you've done that, you need to figure out a way, using just a ruler, that when I launch this, measure whatever I need to measure, then do my calculations, and wham, I should have the initial velocity of that projectile. The projectile is like a little piece of PVC that goes over this. Okay, and that's due, and then also text notes 3, which is homework 5. It's already posted. Any questions on any of these things that are due? Alrighty then.